So hello, uh, let's go back to our next module 5.3, cell compartments and tissue folding with links. Okay. As people get back, I remind you that this course is being recorded and is being live streamed to YouTube at the same time. I wonder if there's any leftovers questions from the are we going to cover parameter scanning today, or will that topic be dropped? We hopefully will cover it today. Okay. We still have one module after this one, and James Luca will talk about this and some other things as well. Okay. Can you visualize cells trained these models? Yes, you can. Yeah, well, your question assumes that the cells are being pulled, right, in a specific direction, and I assume that they are being extended that direction. There is a tracker called moment of inertia tracker where you can get it, you call, and then you can get the major and minor axes of inertia of their cell, so you can get a sense of how long the cell is stretched in a given direction. So you can divide that by what the cell was supposed to have elongate in that direction. So you get this number, and you can feed this number right into the scalar field tracker plugin, and then you should be able to see the strain of the cell. So the link for this presentation is already on the student materials. Okay. You can also add strain as pressure, right? So you can plot. You can also right, that's not strain, right? You can also get the pressure of the cell by making the difference between the current volume of the cell and its target volume. Okay, and that times the lambda, so that should be the pressure of the cell, which either be compressible or it cannot be positive or negative. Okay. The problem with the model inertia is that basically is approximating your cell shape to ellipse, right? That may be not what you want to do. What you want to do is actually the cell shape, but then you have to kind of go over all the pixel locations of the or your cell and see the one that's most to the right, the most that's one or to the left, and then get the actual length of your cell in a specific direction. Yeah. Okay, that's a good question. Answered by Pedro. Okay. Ellipse is good enough. Okay, then it makes your life easier. Okay. I believe I'm sharing screen. Am I not? Okay. Is there any other questions before we start?
Can see your screen.
You cannot see my screen. Can you guys see my screen or not?
Yeah, we
We
can
can
see
see a PowerPoint presentation.
Yeah, it should be a PowerPoint presentation, and this is the Zoom logistics.
Yep, that's right.
Well, now I see it. Yeah, thank you.
Okay. Okay. All right.
You are muted, Julio.
Oh, how do I mute myself? Okay. So
Alt
so
A,
here,
maybe. Maybe you pressed Alt A. Alt
okay, it can be. Can you hear me now?
A. Yes.
Okay, good. Um, so the objective of this model is to make a simple model on epithelium, and then make this epithelium apically constrict and induce a furrow formation. Okay, not completely fold. Well, I know that I said fold at the beginning, but we're gonna just create a furrow. Okay, to make it actually fold inside, you have to add more stuff. You can try that later. Okay, So usually you have an epithelium, right? So the first thing you have to do is build an epithelium, and an epithelial cell is usually made of have an apical side, a basal side, this lateral. So to build this epithelium that you are trying to fold, we have to actually use the notion of compartmentalized cells. Okay, you have already seen a little bit that in the cell migration, but I'm not sure if you actually have seen 2 or 3 or 4 cells that are compartmentalized together. When you do, you have to be careful about how to set up your contact energies. Okay, so these are some examples of epithelial tissues undergoing morphogenesis. So some structures that, well, their cells are compartmentalized, have an apical basal side, and sometimes those tissues can undergo changes like this folding process that you see on, for example, neurotil development. On that one, you have many folding events actually going on here, and or something a little bit simpler, which is endosophageal gastrulation, where those cells of the ventral mesoderm apically enrich the rectomycin network, and that leads to contraction of that size and furrow formation and further invagination of those tissues. Okay. Is there a role of curvature in the fold? Probably there is. Okay, so those are topics under investigation, and that really depends on which system you're talking to. Okay, and of course, then different people have different opinions what's going on. Okay, but here we'll talk about tissue furrow formation or folding in general terms, right? It's up to you guys to adapt to your specific scientific question. Okay. So if you want to model epithelial tissues, if you not only care about that the cells will be elongated, right, as you can use with length string, but the different sides of the cell should have different properties, then you want to actually think harder about the apical side of the cell, the basal side of the cell, and what's not either apical or basal, which is the lateral side of the cell. So epithelial tissues are apically basal polarized, as we talked before in the first day of the course. I talked a little bit about this. So maybe you want to set our cells, subdivide our cells into compartments, and call one apical, one basal, and one in the middle, which you just call lateral, and assign different properties of each one of those compartments. Okay, so usually the apical side faces the lumen or some cavity or some fluid. The lateral side of the cells is actually in contact with the neighboring cells in the epithelia, and they have tight junctions. And the basal side cell is in contact with the ECM or other cells, that if you are talking about stratified epithelia. So, but still, it has different characteristics than the side of the cells or the apical side of the cell, right? So here you want to do two things. First, create an epithelium, a stable epithelium, and then once you find a stable epithelium, which is actually some kind of work, you want to instruct this epithelium to actually apically constrict along some of those cells, apically constrict and deform the tissue. So the objective of the model is to end up with a simulation that looks like this. Okay. So what you can see here, you have a line of cells, right? That each one of those cells has 3 compartments. Okay, so it has an apical side in red on the top, a lateral compartment in the middle, and a basal compartment in blue at the bottom. The apical side sees the medium or nothing, and the basal side see this whole grayish thing, which you call just the ECM. Okay, it's kind of very thick ECM in this case, but this is a toy model. We just want to make something very simple for that you guys can play with. Okay, and what you're not seeing here in this movie is that there are actually links between all those red compartments, which are the apical compartments of those cells, and all those cells here within this region outlined here. At some point, they decide to, we assign different properties to these links, which drives the tissue to, right now, to those cells to constrict and induce that folding. Okay. So we'll have to using two concepts in CompuCell: the concept of the compartments, how to compartmentalize a cell and make cells of different compartments, and we have to be careful to not the cell, this compartment has to know that this is the other compartment that belongs to it, and you should see this other green here very different than it is its own green. Okay, so you have to, when you create compartmentalized cells, you have to duplicate many of the parameters that we would normally have. Okay, we will be playing with the contact energies to make this stable, and then we will play with the links to actually connect the cells and actually drives those chains. Okay, does it sound good? Okay, so let's continue. So the first thing you want to do is to create a new project where you're gonna create this epithelium, right? So this is the first exercise of this module. So I'll go with this a little bit quick. Let's go to CompuCell3D project, new CompuCell3D project. Let's give the name of our model, module 5_3_ tissue folding. Okay. Hit continue. And now in this general generation properties, you actually want to change those numbers here. So please, you usually have X and Y as 256. I want you to make the X 350 and the Y 100, okay? And the other thing I want you guys to change is to change the periodic conditions or the boundary conditions on the X direction to be periodic. So the idea is that you have a simulation space that's very long on the X, and in this X direction you want the cell here on the end here to actually be seeing the cell on the bottom end. So it's periodic boundary conditions on in the horizontal direction. Okay. And we can leave everything else as it is. Okay. So did everybody do this change? 350 here and 100 here, okay? And the X has to be periodic. So I'll continue. Now the next page, the cell types. You want to add 4 cell types to the simulation. Because our cells will be made of 3 types, and you want to differentiate between what the cell sees on the top and what the cell sees on the bottom. So on the top, they will see, above them, they'll see the medium, and below that, they will see the ECM. So you want to add apical, lateral, basal side, and also another cell type which we'll call the ECM. Okay, so make sure that you type all those things and hit add to populate the table there. And once you have all your 5 cell types, right, the 4 you just add plus medium, then you can hit continue. Everybody with me? So we will ignore the chemical fields, right? And here on the cell properties and behaviors window, we'll select contact internal, focal point plasticity, volume flex, and cell neighbors. And this will be an example where it's absolutely necessary that you guys have the center of mass selected. Okay. So have you seen the contact internal before? Or will this be the first time? Okay, maybe this is the first time. No problems. So did you all select this? Oh, maybe seeing the cell migration model. Okay, we'll be seeing again here. Okay. These slides assume that you have never seen those before. So after you select all this, you can configuration complete. And now we have all the basic elements of simulation, and it's your turn now. Now the first task I'll ask you is go back to the Initializer plugin, delete what you have there, and which should be around line 255. And I want you to create 4 lines, 4 rows. The first row of only made of apical cells, the second row only made of lateral cells, the third row only made of basal cells, and a last row made of big ECM cells. Okay. So to do that, you have to, in the uniform initializer, you have this region inside. You have to copy and paste this region 4 times to create each one of those rows. Okay. And just remembering the origin of coordinates in CompuCell simulations is on the bottom left. So this is the 0, and then you go up here. Okay. So, and here you already see the code I'm using to draw the apical line. Okay, line of cells. When you draw the ECM, it does not need to be those big cells, but it can be also a bunch of cells, which is 7 by 7. So that's your first task. Please go on the code on the Uniform Initializer plugin and try to create this initial condition. Okay. Okay, that's not enough. We're still far away to get a stable epithelium, but this will be the first step. So you basically have to repeat that 4 times, one for the apical, the other for the lateral, the other for the basal, right? And your cells are 7 by 7, so you have to do that in steps of 7. So for this one, I made the minimum and max boxes reached. Well, the X goes from 0 to 350, which is the size of our simulation. And then the Y I made from 0 to 35. And I make the width of the ECM cell to be 35. And then from 35 to 42, 42 to 49, and 49 to 56. So this is one possible solution to actually accomplish this. Okay, so here in my Uniform Initializer, I define these 4 regions, 1 for each row. Okay, and the first one is, it just goes as in this order: apical, lateral, basal, and ECM. And these are the coordinates that I use to draw it. Okay, so after you do this, maybe you have already done by yourselves, you can play the simulation to check if you get the correct initial condition. If you just hit play, it's gonna play the simulation. It's bad if you just hit the step function, so you can see the very first frame, right? The 0 Monte Carlo step to see how it looks like, and just to check if you got it as you want it. So is this making sense? Was this the first time that you use multiple regions in the initializers? No, okay, you have already used that before. Okay. All right, so if you have already have done this, I'll proceed. Okay, so this is the solution. So that was your first task. But if you just play the simulation, you see that things look very ugly, right? So you can try to play the simulation as it is right now, and you should get something that looks like this, right? So what's happening here? Can anyone now tell me? So this is definitely not an stable epithelium, right? What's happening is that, well, the simulations just use the default parameters, and use the default parameters. We did select FPP plugins, so it's just making connections with FPP links through any cell that it sees. Okay, those ECM cells, which I set up them to be very big at the beginning, they still have the target area that CompuCell3D assigns as a default, which is 50. So the first thing they do, they shrink, and those cells do not know who they are. They have all the same contact energies, so they will just randomly mix with one another. Okay, so what we need to do now is, okay, the initial condition is right, but everything that goes after is wrong. So we have to fix all those parameters, right? So first, let's adjust the links, okay? So as I said, by default, the CompuCell3D is going to create a template code with all the possible pair type combinations, right? So here we have how many cell types? We have 4, right? So you can do the calculation how many cell pairs it is, and they are all trying to do something. They are all active, okay? So in this model, we only care about the connections between neighboring apical sites, okay? So the first thing you have to do is, if you're only interested in the links between apical sites between adjacent cells, we can leave that on and turn off all the other ones. So you can either delete or comment all the other FPP links that you see under the focal point plasticity plugin in the XML code, or you can just set the maximum number of junctions to be 0. Okay. And as you have seen before, CompuCell also creates a template for internal contacts between cells that belong to the same cell. We will not be using that today, so you have to also turn all those off, okay, including the internal parameters for between apical and apical sites. Okay, so the apical we're gonna leave that on, and usually each apical site cell see 2 neighboring apical sites, one to the left, one to the right. So we want to have our maximum number of junctions to be 2, and but that's between cells of different types, not between cells of the same type. Okay, each cell has only one apical compartment, so we can ignore the apical pair for internal compartments. Paulo Burke has a very good question. Would not work the lateral sides? Why? So if the cells are connected by the lateral sides, shouldn't that be turned on in our model? Okay, so that's a good question, but the region of the cell which actually has the additional junctional belt, yes, is technically on the lateral side of the cells, but is very close to the apical side. So this is one case that our terms do not completely match the biology, because the lateral junction is very close to the apical side of the cell, right? Is right there. Is better, our model be more realistic to have those links from the apical compartments in our model than from the lateral compartments for our model. Does this make sense? So this is a case where the organs don't completely match the biology, but we have to make it, we want the apical side of cells to the side junction of cells to be between the apical side, because that is the it will be more closely it better matched what's seen in vivo, and will make a big difference. Would it hurt leaving both? You can leave both, and you can tell us what happens. Okay, that's okay. Because usually the very strong complex junctions, the ones that actually transmit the force between the cells to one another, the form is happening right at the top. But it's true that you also have other types of junctions all the way to the lateral membrane of the cell. You have the desmos zones, you have other kind of junctions. So it's justifiable to have links between those lateral compartments as well. Okay. So turn off all the links except apical, and if you want, you can also leave the lateral as well. And so that's one fix, our simulation. And the other fix that we need is, if you're using very big ECM cells, you have to adjust their target volume. So it should be 35 by 35. So the target volume should be 1225 pixels. Okay. One thing that may help your simulation, you may want to set the lambda volume of the ECM cells to be very low. Instead of 2, you can make 0.2. That will make your simulation look a little bit better than what I'm showing here. Okay. All right. So is everybody on board here? If you're all fixed, you should get something that looks like this. Okay. So yes, did you got it? Did you guys got something that looks like this? Now the ECM cells do not shrink, and all your apical cells, they're not compartments yet, are linked with FPP links.
Excuse me, can you show the previous slide? Because my...
Yes.
Okay,
Yes.
it shrinks for me, the ECM.
Okay, so you have to go to the volume plugin and fix the target volume. And of course, you have to make sure that you save the simulation before you go to the player. Can I go back?
Yeah, sure.
Okay, great. Okay, are your initial ECM cells very big, or they are 7 by 7 initially? If they are 7 by 7 initially, you leave the target volume at 50. Maybe that's what happened. So, do you need help? If you need help, someone can assist you in the breakout room. For formatting error, okay, so maybe something was not set up right in the plugin tags. That's something like this. Okay. So if anyone could help Ajay in the breakout room and Tahim, I would appreciate. Okay, Juliano can help you both. Thanks, Juliano. Okay, so I hope you all got something that the rest of you got something that looks like this. Okay, but as you play simulation, you see that those cells start to move around. Okay, you can even tell which ones started together. They're just moving around, and they do not know that they belong to the same cell, basically. Okay, So the next thing that we need to do is go to the Python code and instruct those cells that, okay, you three one that are on top of each other, you actually belong to the same cell. Okay, so you have to do that on the Python level. Okay, so you basically have to find all the cells that are stuck together, okay, and tell them you belong to the same cell. So usually each one of those cells that you create, they have an ID, but they also have something that's called a cluster ID. Okay, so if you want to make group a bunch of cells together to belong to the same cell, you have to all assign them to the same cluster ID. And there is a function to do this in CompuCell. There is self.reassign underscore cluster underscore ID, and then the name of the cell that you're reassigning and the new cluster ID that it has. So in this case, cell 2 is getting the cluster ID of cell. Okay, so I'm reading the cluster ID of my original cell and assigning it to the cell 2.
Excuse me, what is cell 2?
Cell 2, okay, that's code specific. Okay, is the name of your cell. It can be the neighbor, it can be another loop over other cell type. So, but before you get there, we have to first identify all the cells that are on top of each other, right? So how you identify all the cells that are on top of each other? Does anyone has an idea? Is there any suggestion? You can look through a type and look for neighbors or the other type. Very good, Paulo. The other complemented, same, XCOM, excellent, get COM. With the angle like last module, that can be done. But maybe look at the center of mass a little bit easier, right? So that's actually what I suggest. Do looper over one cell type. Inside that loop, add another loop for the other cell type, and check if the both x coordinate center of mass are equal. Okay. If you'll be doing that on the start function, then the cells have not moved yet, so they should match the center of mass if they're on top of each other. And then if they are, you just use the function that you have at the bottom there. Okay, so try to do that and see if you can, if it works. Okay, that's true what Pedro said. Checking the neighbors, close neighbor of certain type would work for any rotation. Yes. So if your epithelium was like this, right, that would be a very general way to do it. But here it's oriented in the x direction, so it's easier. Okay, so let me show this is one possible solution. Okay, so I'm just implementing what I did. I chose to start with the apical side. I'll go over the list of all the cells that are of type apical side. And inside I do two loops actually. The first loop for all the cells that are of the lateral side. I compare their center of masses, and if they are exactly equal, I link those two cells. Well, that's a good question, Arhan. because the cells will wiggle. But this is being done in the start function, okay? And in the start function, the cells have not, no pixel copy attempts have happened. So you can count on the center of mass to be exactly equal. Okay, but yeah, but if it was something a little bit different, then yes, you have to check there within a interval. That's true. Okay. So I'm doing a loop for the first cell type, and then I'm doing a loop for the another cell type. If you just pull up those loops from the CompuCell menu, you're gonna give you for cell and for cell. So you have to make sure that the second cell type does not get, the second loop does not get mixed with the first cell loop. So that's why I call this one cell and this other one cell 2. Okay, so they have to be different. Okay, and then I check cell 1 if equal to cell 2, the x center mass. Once I found that, I can stop the loop because all the other cells will be different. Okay, so there's no, so this break here takes you out for the innermost for loop that you are in. So it's gonna take you out from this loop, but you keep you still in this outer loop. Okay, and then I link the apical with the basal, with the lateral, but I still have to link the apical with the basal side. Okay, so I do another loop here with looking for all the basal cells and do the same code again. And when I do this, this is what I have. For this simulation, I only have instruct the player to draw the cluster borders and not the cell borders. So here you can see that the cells are actually made, all those cells here belong to the same cluster. And this one belongs to the same cluster and this one belongs to the same cluster because I have a different kind of boundary drawing to show them.
So in the reassign cluster ID, the second parameter, I mean the cell cluster ID, is copied to the first parameter.
Exactly.
Oh.
Exactly. Yes. All right. Okay, so now if you do your simulation, they should look a little bit better at the beginning, but everything that you have seen on the first one and the one before, it will still happen. The cells now know that they belong to the same cell. Those compartments know that they belong to the, to which compartments belong to the same cell, which parts is from the other cells. But we didn't, besides this, we didn't change any of the parameters of the energy or the links or so forth. So the cells will still mix over time because they don't have any strong attachment to the cells of the other type. Okay, so what you have to do now, you have to adjust their contact interactions in order to prevent this mixing. Okay, and that's the key step to make sure that your epithelium will be stable. Does it make sense? So, and now it comes to the part that may sounds very complicated. So, because now we have cells that may be of the same type but belong to, so we now have this also cell types, apical, lateral, basal, right? But at each point in time, one of these compartments are seen compartments that belong to the same cluster and compartments that belong to a different cluster. Okay, so they should have different contact energies between them. Okay, so this means that when you look at our contact energy table, we actually have two contact energy tables. One for all the pairs of cell types that belong to different clusters, and another for all the cell pair types that belong to the same cluster. Okay, so you have all these different numbers to specify. Does this make sense? So it's one thing, this interaction of this green with this red, and a different thing, the interaction of this green with this red or the apical side that belongs to the same cell. Okay, so all your contact energies suddenly got double, and you need to know which values to put there. Does it make sense? So, in other words, okay, now we are dealing with a lot of parameters, okay? And that seems to be, we're gonna spend the rest next 5 days trying to fix this, but we can reason out what those values should be, okay? So let's go now step by step and think about it.
Can you say again what's the problem here with the energies?
Well, the problem here is that now you have a lot of parameters, basically. If you just run simulation as it is, you know that all those numbers here are equal to the same value, which is 10, and that means that the cells are really just mixing. So now we have to correct those numbers to actually have different contact energies between cells of different types and between cells that belong to, and you have to differentiate those contacts of compartments that belong to the same cluster and contacts that belong to different clusters. So that's why now we have two tables of contact energies. Okay, so let's now go step by step with what those energies should be. So we can start with the internal compartments, right? So one thing that we know for sure is that all those cells, all those compartments that belong to the same cell, they should be more closely in contact with one another, right? They should prefer to be, you want to ensure that our cell cluster that's made of different compartments, it's well connected together. So we should prefer to be in contact with the compartments of the same type, of the same cluster, than with contacts with other clusters. So one thing that you know for sure is that probably when you choose your contact energies, you want those values to be low. So to ensure that the cells remains a single thing, okay? So you probably want all those values here to be low. Does it make sense? Okay. Yes, okay. Lucas brought a very good point. All those cells here, they should only have one copy of each compartment, right? So we do not care about all those values in the diagonal. Okay, so that already simplifies our life, because this one here, and this one here, they will never be used. So you can just set it to 0 or don't bother changing it. Okay, so you can set all those values to 0, just like you never had two mediums in the same simulation. So that first value of your contacts, either external or internal, which medium, you can just ignore. Okay, so now we solve. Okay, so we know that this has to be low because we want to ensure that they like each other, and those here in the diagonal, we don't care. Okay, so we already solve one, and then yeah, if you have a value there but it's not being used, it's no problem. The other thing is that there are no cells with a medium compartment or cells with an ECM compartment, right? The ECM is a cell by itself that is not part of any cluster. So one thing that you can do, you can basically ignore all the values that are in the contact internal that relates to the ECM. So that, together with what Lucas said, makes our life already very easy. So in the contact internal table, we only care about 3 values: lateral apical, basal apical, and basolateral. These are all the 3 values that we have to specify, because, and we don't, you know that they should be low. Okay, you know that they should be low. Does it make sense? So here you have to be using all your what you learned on the first day. Okay, So, okay, we solve the internal content of energy values, right? Or we know more or less how they should look like. They should be a low value there. Now you have to leave the other energy elements there. I think that if you just delete those entries, you get an error, okay? You just set all of them to 0 or just ignore them, okay? So remember this black this matrix is symmetric, so that's why I blacked out all the off-diagonal elements, okay, in the bottom. Okay, now let's go to the other table of contact energies, and now this one is going to be a little bit more complicated than you have before. So let's start by, so what's the first thing you can reason out? What about the contact? Let's talk about the diagonal. Okay, the diagonal, which sets the addition between apical, lateral, and basal. Okay, there's a question: why low energy to apical basal? Okay, I was trying to keep the story simple here and say that because they belong to the same cell, you want them all to be low. But yes, you want the apical to be one side and the basal to be on the opposite side with the lateral in between. So one thing that you can do is can make the energy between apical and basal to be a little bit higher to ensure that this happens. Yes, you can do that. It's a good question. Yes. Especially when you have a situation where your epithelial cells are moving a lot for some reason, or they are going into and out of the epithelium because they're that's what the cells do when they divide. So the cells in the epithelium, when they divide, they lose their connections. They all go to the basal side, round up, divide, and then go back in. Okay. So when you have the situation, you probably want to make sure that the apical and the basal sides will sort out as the cell elongates. Okay. Yeah. But here the cells are not moving; they're just kind of relative to one another. So it's okay to just leave the apical base to be as low as the others. Okay. Okay, but let's go back to now the cross cluster to cluster interactions. So let's see what should be the energy between apical and apical, lateral and lateral, and basal and basal. Okay, should they be high or low? Or another question: do they like to be with one another? Okay, does everybody agrees with Paulo, or do you have something to add? Okay, so should they be low, as low? Very good, Lucas. Yes, it has to be low, but slightly higher than the internal, right? You don't want it, otherwise you may start having mixing, right? Otherwise those two can swipe to other. So we want them to be low, but we want them to be low but a little bit higher than what you had before. Okay. If they're low, if they're high and everything else is low, they'll be detached. Yes. So everything here is relative to what the other energies will have been chosen, right? So, but let's go side by side. Okay. So the cells like to align their apical with the lateral and the basal. So you know that they should like this. Okay. So that also should be low, but maybe a little bit higher than what you had for the internal. So I'll put these things here as low plus. Okay. Something like this. Does it make sense? I mean, what I'm basically saying is that, okay, those cells like to align themselves apical, basal, right? but they should not like that so much that they would want the compartment to enter the inside the other cell. So that's why they have to be low but higher than what you have internally. But the basic answer to your question is yes, they will move apart. Okay, so what else we can say? What about the adhesion between the apical and the lateral, or these cross terms here? And basal and lateral, should they be high or low? So would the cells like to match the basal with the lateral, or the apical to the other one? Or what should be the adhesion energy between apical and basal? Should they like to be close to one another, or should they hate each other? Okay, should be higher. Okay, so yes, all these crossings, they should be high energies. So they do not like to have, so use this kind of contact here that you see the red from this side entering contact with the lateral of this side should be penalized. So this may still happen during the fluctuations, but you quickly go back to what you have here on the right, which is just apical and basal. Okay, so when you have this, so all this now is ensuring this kind of shape. Does it make sense to everyone so far? What else we can tell? Okay, so what about the apical interaction with the medium and the ECM? Okay, now we will get to XML later. Let's first figure out qualitatively what's going on. Okay. So we have to reason out what should be. Yeah. Of course, we could go to the XML code directly and just try numbers randomly, but it's better if you think about what should be what's the behavior should be, and based on what the behavior should be, what should be the relative values of those things, and then we go to the code and try to implement that. So let's talk about now the apical side. So the apical side is mostly done, but you still have the apical with the medium and the apical with the CM. One of them should be this high and the other one should be low. Which ones? Okay.
Apical with the medium should be the same as the basal with the ECM.
Yes, very good. By the same logic, and that they
would be
like
lower,
that, or should they hate that?
They should love them.
Yes,
like lower and
love them. Yes.
But the vice versa, like the apical with the ECM or the basal with the medium would be much higher.
Yes. So other people already gave the same answer. So apical should be low here, and apical ECM should be very high. Okay, to make sure that the cell never flips. Okay, you probably don't want to be as low as the internal one, maybe just as low as the apical to apical. How about that? Okay, and now the same thing for the basal side, you have the same logic but inverted. Okay, basal with medium should be high. They should never like to be here, but they should like to be here. Okay, like this. Okay, and now we have those other 4 missing. What they should be? So, well, ECM and medium should be super high. They should never touch each other, right? We want to ensure that you always have cells in between. Okay. ECM does not make much sense, right? The ECM, we subdivide the same into different units, but they should be the same tissue. So the ECM itself should be 0. Okay, so this value here should be 0. And the lateral side with the medium and the lateral side with the ECM, maybe should assign the same value as with the basal and apical side of the neighboring cells, something that's also high. So like this and this. And with this, we set up qualitatively what those relationships should be. Okay? So is this all making sense? Or do you disagree with one of those parameters? So I tried to reason out what all those hierarchies should be. Okay. Now that we reason out all those hierarchies should be, and I hope you you kind of agree. You said basal ECM low, but they are merging. Okay, now it goes to the other question, right? Now that you have this qualitative table of things, let's try to put some numbers that reflect that and see what happens. Okay. So you can do increase of 5. Okay. Well, if you just if the difference between additions energies that you put there is just like they're all 10 at the beginning, and just make 11, 9, 8. So that's not enough of a difference to see an effect. The difference has to be a little bit higher. Okay. So, well, in the interest of time, I will just show the values that I used. Okay. So the content internal I just set to 2, a very low value, so they really like to be close to one another. This low plus that we defined before, I just set it to 5, so it's still low, but as before. The high values, or the higher values that we set, we decide to just leave it, left it to be 10, and those very high values I just left to be 20. And I can guarantee you that if you make those choices of numbers, you'll get something that looks like in my picture. Okay. So,
Sorry, about the internal other parameter that you put dash. So we are going to delete them, or what should we do with them? Or
I think I'm pretty sure that if you delete them, you get an error. You just leave them wherever they are. They're never used, so that's why you put a dash, because they're never used. So you can either set all of those to 0 or leave them to the default value, which is 10.
The default value is 10, so it may have an effect on the simulation.
You can leave there because they're never used. Those pairs never happen, right? So people are saying that the basal ECM at 5 is not working. Okay. Maybe you can make the well, I instruct you to set the ECM to be 0, right? If it's not working, maybe you can increase a little bit. In principle, should work for. It's fine now. Okay, good. Okay, so is this working for everyone? If yes, you just said yes in the chat. Or maybe do you need a little bit more time to type in those values? Okay, some people are saying that the basal layer has been ruptured. Okay, that did not happen in my simulation. Double check if you have the correct values. Maybe this is not a good solution, but so do you have a basal that just starts float around? Make sure that the contact internal between basal and lateral is set to 2, because this value here should prevent the basals from detaching. Okay, if for everyone the base is starting to mix with ECM, maybe you can increase this contact here from 5 to 10. Maybe that will fix. Yeah, as James says, you can also try different energies. In principle, all that hierarchy that we have here should be enough. You can improve on that to make it better. You can make arguments that, well, all those low plus should be a little bit different from one another, but that's the simplest things I can present to you, propose to you guys. Okay. So now we have hopefully a stable epithelium. If your basal ECM is wandering around, make sure that you have increase its value with the ECM. Yes, ECM has to be 0. Maybe that's what's missing. Fixed. Okay, excellent. And now let's actually add some active movement to this thing. Let's start to follow the tissue. So you can see that only make this thing was already a lot of work, right? Even though it was doing nothing. But now we have a stable epithelium. And in order to get a stable epithelium CompuCell, we have to really think through, okay, what those energies should be, what they should be the contact energies. And so it takes some time. You have to know what's going on, right? You have to understand what the contact energies work. So that's what I try to emphasize on the first day of this CompuCell workshop. Okay, so now we have our stable epithelium with a nicely connected apical side by side on the top. What you want to do now is actually make that fold, okay? So are you all ready to do that? If you are, then let's do that. And to change those links properties has to be done inside the Python code. But before you go to the Python code, you have to remember tell the plugin that you'll be changing then from the Python code. So in other words, you have to go under focal point plasticity and uncomment the local tag. So the change you'll be doing from the Python level will be accepted by the CompuCell3D player. Okay. Good question, Jay. To make the cells, okay, what if you want control of how tall the cells are or short the cells are? Okay, there is a way to do this. You can actually use those links to make the cells shorter or bigger. Okay, you can go back to the focal point plasticity settings in the XML code, and you can draw links between the apical side and the lateral side, the basal side, and also add a link between the basal and the apical side, but within the same cell. Okay, so remember all those FP links that will have internal parameters, they all refer to the compartments that belong to the same cell. So you can add a set of links between those compartments and change the target distance of those links to make your cell either longer or shorter. That will do that artificially, but how about as a consequence of cell adhesion? It probably can work. I never tried that because the other way gives more control, but that's something that you can try. Definitely. Maybe decrease the adhesion between green and green would help that. You can also change the target volume of those compartments, right? You can also do that. Right here, you're making the apical side 7x7, the lateral side compartment 7x7, and the basal side 7x7, but the lateral side probably should be bigger and the other ones smaller, right? Well, just increase the volume will also do the trick. Okay, so there are probably many ways to do it. Okay, so very good questions. Okay, so we turn on the local tag to allow changes in the Python level of coding. And what you want to do now, you want to do this not in the start function but in the step function. You want that some specific you want to create epithelium and let it be there for some time, and a specific time tell all the cells at the center to apical constrict. Okay, so let's say that, so this is something that you want to do at the step function, right? So what I want you guys to try by yourselves is at specific time, let's say at Monte Carlo step equals 500, find a group of apical compartments inside the epithelium, right? You can choose where it's going to be and how wide it's going to be. Okay, find all of them, and for all of them you delete all the links that they have and create new links with their apical neighbors. Okay, and for that you'll be using those two drop down menu codes, the delete FPP links, right? So you find the cell that you want to change, delete the FPP links, and then after you delete, you go over the neighbors, find the neighbors, and make a new link with those neighbors. If someone could help Cicely to, I will appreciate. So as James says, the reason the cell elongates or is partially because of the microtubule structure inside the cell become polarized, and so these are long pipes inside the cell basically that they're very rigid and they are centrally organized in the centrosome, very close to the nucleus of the cell, and they in an elongated cell, all those microtubules, they make some kind of hourglass shape, right? And there's some that goes to the apical side, some that go to the basal side, and they help keep the cell elongated. So in some way, that's using links as a surrogate for the elongating, or as a surrogate for the underlying microtubule structure is is very justifiable. Okay, so try to make your code for yourselves. I will give you 1 minute and then I will show my solution. In many cases that will be true. The microtubes drive the elongation of the cell. In other cases, that's not true at all. Sometimes the cells become elongated because of external factors, and the microtubes are still aligned inside the cells, but they just align as a result of that elongation. So that's happening from the epithelial cell. Well, in Drosophila dorsal closure, you have a group of cells that contract and drive all the epithelial side to elongate. And if you look at the epithelial side, they're very elongated, and the microtubules are aligned in the direction of elongation, but that happens as a consequence, not as a driver. So, well, the thing is that, well, in biology, you always can have find exceptions if you look at half those things. Someone propose a model or a mechanism, and then people find many other instances that that's not the case. But usually we can make the argument, yes, the microtubes are helping keep the cells elongated. Okay, so did anyone got this working already? Yes, no? Let me try the chat. So are you done with the exercise? Okay, the lambda distance value. So that is how strong it is. You can just keep at 10. Oh, that's a good question. Try 10. If nothing works, keep setting higher. You can start trying with 20 or 30. Okay. The target distance has to be something that's lower than 7 in order to drive contraction. A change. You can just set the target distance to 0. If anyone got the tissue to fold or get some indentation, please paste that on the Slack. How to justify this plugin biologically? Okay, so biologically, when the cells undergo invagination or this kind of folding, is because 90% of the time is because there is an actin cytoskeleton with a set of filaments, okay, that are present at the apical side of the cell that becomes activated, and they start to contract the apical cytoskeleton. Okay, the axon cell contract. But the apical cytoskeleton on the top of the cells is connected to the tight junctions around it. So when they contract, they pull the neighbors. So what's happening is that the cell, the top of the cell, the apical cytoskeleton start to constrict, and as it constricts, it's pull its cell neighbors. And when many cells are doing this, then this causes the whole, each one of those cells to become a wedge shape because you constrict here. And when you have many of those cells in the same region, trying to get this wedge shape, you end up driving the curvature of the tissue. So that's what's happening biologically. In the model, you cannot directly model the actomizing cytoskeleton in the apical size, but you can model its downstream effect, which is pulling the other cells together. Okay, so when the cell apical sig is pulling the other ones towards it, right, exerting forces. So you're just modeling the net downstream effect. Okay, we are pulling the other cells, and then when you make this, you drive tissue folding. Yeah, so after you delete the cells, you have to do a loop over the cell neighbors, find the neighbor that's an apical compartment as well, and then do the link. So let me show my code. Okay, so again, this is one way to implement it. Your code may look very different than what I have here. So yes, you have also checked if the neighbor is not medium. Good. So let me walk you through my code. So I check what is the Monte Carlo step. If it's equal 500, I do a loop over all the apical cells, right? These are the ones that have the links. And then if the cells are between the center of mass, the x direction center of mass is between this range, and you can make this bigger or smaller, right? You first remove all the FP links of the cells. And once you remove the out FP links of the cells, you have to reestablish those links. So I do a loop over my neighbors. Okay, that's this familiar one. And if this is a neighbor and not a medium, and if this neighbor is of type self-apical, then I create a new link. And here I define the lambda distance to be 40, for example, the target distance to be 4, so it has to be smaller than 7, otherwise face will look funny. And I kept the maximum distance to be 20 pixels as I had before, and I used those 3 numbers here as arguments of this function, and then the first entry here is the cell, the second entry is the neighbor. Okay, and I promise that if you do this code here, you get something that looks like this. You get some kind of indentation here, and the cells kind of moving inside. Okay. Yes, yes, Ajay. Yes, I think that would be a way to accomplish it. This. I'm not sure I understand your question. Membrane is tight domino structure. Yeah,
Anything that happens in a domino line can affect all the next ones. But this is so dense that anything that happens anywhere should have some effect on the whole line, no?
Yes, that's true. That's true.
Just an observation. I know it's out of the programming here.
No, it's true. We do have a closed system here, right?
Yes.
I made those.
Too close. It's very tight.
Yeah, I made those cells here to be seeing those cells here, right?
Yeah.
Yeah, but all those cells feel this thing happening here. Yeah.
Right.
It takes some time for them to feel that, right? As it starts to pull, well, you can see in simulation that it takes some time for the cells to actually move, but they will be sensing that thing.
Also, the edge effects are,
Mhm.
there are some kind of walls here, no, on the right and left.
No, because we set periodic boundary conditions, right?
Oh,
So
okay.
it continues on the other side.
Okay,
But
fine.
still, all those cells are things. So that's why I tried to make this very big in the horizontal direction to kind of reduce a little bit. Because if the simulation was just centered between 100 and 250, right? Those cells that are not constrict, they will have to stretch a lot, right? And there is always this tug of war. Okay, for some cells to constrict, the other cells have to give way a little bit. So if you go back to the XML code and make those all those cells to be very high lambda volume, lambda strength, right? To begin with, those cells that said they would not be able to constrict, we have to even increase more their lambda. How can you do a full invagination? Okay, that's a good question. First, this model is a little bit simplified, right? One that thinks that one thing that you probably want to do, you want to make the apical compartment a little bit smaller on those cells that are undergoing constriction, right? Otherwise, you have some volume exclusion mechanism there getting in the way. Okay. Some people, at least for Drosophila gastrulation, some people said that there should be tensions, transverse tensions happening on the cells for this to happen. So the cells either have, not forgot the way it goes. You probably have to try to force those cells to shorten a little bit, and that will help it drive it even down further. Okay. You also have some kind of volume exclusion because of the ECM below it, right? So you can try to make the lambda volume of the ECM cells that you're modeling below it to be very low. So if you make from that, right now it's 2, you make it 0.2, so they are very compressible. That you should help a little bit that tissue to go inside more. You can also make those initial cell links from the other side, they're not seem to be a little bit weaker, so they can stretch more. That should also facilitate the process. Okay, what else you can do? This is a good question. How you can get a full vagination, right? So some people get that there must be things happening on the transversal side. Okay. So you can add those links from the other internal links to make the cells longer or shorter. Only the cells that are undergoing vagination, see if it helps. So I think I stopped screen share, but that's basically everything that I had for this module. Are there more questions? So how to get full imagination with this very simple model is it's a very good question. I just suggest a bunch of things you can, guys. You are free to try yourselves. What else you can you can do. Okay. So So I know that there was some interest in those PCP kind of simulations. Maybe I can set a time tomorrow to show you guys. I didn't really prepare a lecture about that, but I can show a code that I have and walk you through what's going on. But it's basically using all those concepts that you have seen before. Here, you're using compartment cells, and you are making educated guesses of how the energies should be in order to drive kind of compartments of different size to be in touch with others. Okay, so if there's interest, I can set a parallel section tomorrow to just go over the code and tell you what's going on. I know that says something like this for other topics, and we can set up a time tomorrow. Okay. Yes, I said I will make an exercise about cells using the anchors to drive the cells and make another anchor and drive the cells. That would be the idea. It's just that, well, I didn't get into doing that, and we are already running out of time anyway. Okay. So, but in principle, tomorrow there is no lectures. Is the hackathon, right? So you're gonna put all this in practice for those different projects. And I heard all your projects presentations on yesterday or Thursday, and they all sound very exciting. But there's still one more module to go that Jens Luke is gonna show how you do other things with CompuCell. I don't want to take too much of his time, and I will stop here and let him take over, or maybe I think probably need a break in between.